Okay, let us discuss problem 1.194. So in this problem we are going to discuss two methods for finding the angular momentum. You can find angular momentum by two ways. So two methods for finding angular momentum. So let me read the question what this says. This says a light non-stretchable thread is wound on a massive fixed pulley of radius r. So I have a pulley. Let us say this pulley is fixed, and this pulley will have, let us say, massive. So let us say moment of inertia of this pulley is I. So this is a massive pulley, and a small object mass m is tied to the free end of the thread. So there is a thread, and this thread contains a small object m. Are you getting? So mass of this object is m. That is basically hanging over one end of the thread. Another end is basically tied on the pulley. Now the question says, the system is at the moment t is equals to 0, system is released. So system is released from t is equals to 0. So system is released at t is equals to 0. Now you have to find, starts moving, find the angular momentum related to the pulley axis as a function of time. So we have to find angular momentum as a function of time about axis of pulley. So this is my axis. So let us call this as a O. So we have to find angular momentum about O. Are you getting? So this is angular momentum about O. So we have to find LO as a function of time t. So this is the thing which we have to find out. So how we will proceed? One way to proceed is that we can basically use this expression dl by dt is equals to torque external, and then I will do integration. Now t is equals to 0, I can say the system is in the rest, so angular momentum is 0. Nothing is moving, no omega, no angular velocity, so angular momentum will be 0 at t is equals to 0. Now see, what are the forces that is acting on this system? If about O, because I am interested in angular momentum about O. So you see, what are the forces that is acting? There is the axial force that will pass through this point. Mg of this disk that will also pass through this point. So no external torque is going to be created by this force and this mg. Now let us say this mg. Of course, this mg will create a torque, and this distance is given to you. So let us say radius is r. So this will create a torque mg into r. So now I can say torque external in this case is simply mg into r. Are you getting? Now so if I integrate dl is equals to mgr into dt, and if I integrate this 0 to L, 0 to t, so I will have L is equals to mgr into t. So this is my result for angular momentum about O. Are you getting? Same thing we can derive using another way, that we will not use dl by dt, we will simply find angular momentum. So let us try to find angular momentum as a function of time without using dl by dt is equals to torque external. Now the second way to find this is writing motion of equation. So we will have this system, this block is here, let us say mass m, forces acting is mg here, we will have tension here, and one tensor will act here. Now let us say this system is going down with acceleration a, and this acquires a angular acceleration alpha. Now I can say this is a case of pure rolling, because this point I can find acceleration a. So this point on the thread has acceleration a, and if I consider the same point on the disk, this will have acceleration alpha into r. So a will be alpha into r, because I can consider this point either on the thread or I can consider on the disks. So I will have a is equals to alpha r. Are you getting? Now if I write equation of motion, so one equation I can write. You can do yourself also. So I have one equation I can write, because this is going downward. So mg minus t is equals to mass into acceleration. And if I write for disk, so torque T into R this is the torque about this point O. So torque is equals to I alpha. Alpha is A by R. Are you getting? So I can write tension is equals to I into A by R square. And if I plug this value here, so we will have mg minus t. T is I A by R square. This is equals to ma. So from here we will have A is equals to mg divided by, so I1 plus m plus, you check yourself, m plus I by R square. You check, you will get the same result. You can write in the same way, A is equals to z divided by mm goes, so 1 plus I by m R square. So this is the acceleration of this particle. So let us find velocity at after time t. So velocity, initial velocity, I am interested in finding velocity of this mass. So let us say this mass is here. So let us say velocity after time t is v. So I can find v is equals to initial velocity is 0 u plus at. Now I know the a, z by 1 plus I by m R square into t. So this is my velocity. So I can say angular momentum of mass m is, angular momentum of mass m. So we will have angular momentum of mass m. This will be equals to r mvr. You see here. So we will have velocity is going in this direction, and r is this distance, point this perpendicular distance from point of axis. This is this distance. So mass is m. So we will have mv into r. So it will be simply mvr. R is basically capital R here we will have, because in the first part I have written capital R. So angular momentum initially at this point of time for this small mass is mvr, and v is given by this expression. Let us find angular momentum of disk or pulley, angular momentum of pulley. Now angular momentum of pulley is simply I into omega, because this is simply rotating, so I into omega. So what is the total angular momentum about O? This will be mvr plus I into omega. Are you getting or not? Here we should have r, mvr. So let us write, so angular momentum will be about O, this is mvr plus I into omega, and omega is nothing but v by r. This is a case of pure rolling. So mvr plus I and v by r, omega is v by r. So if I take vr common, so let us take mvr common. So what we will have, if I take mvr common, I will have 1 plus v is there. So I will have I by m R square. So this is the angular momentum, total angular momentum at any point of time. Now the velocity is given by the expression, first equation you see here. So I have already solved for velocity. Velocity is given by z by I plus m R square into t. If I plug this value, so I will have m into r into this value 1 plus I by m R square. And now my multiplied by velocity, and velocity I have z divided by 1 plus I by m R square, and on the top we will have time also. So this term and this term gets cancelled out, so we will have mgr into t. So you see angular momentum about O is same as mgrt that we have found in equation number 1, but that time we have used dl by dt is equals to torque external. So this problem suggests me I can find angular momentum directly, that is the angular momentum mvr plus I omega, or I can use change in angular momentum is torque external, that is dl by dt. So time derivative of angular momentum is equals to torque external, and I can integrate that equation. From there I can get the angular momentum. So there are two ways by which we can calculate the angular momentum. Either I can use dl by dt is equals to torque external, or I can use to find angular momentum of each particle of the system separately and then finally add. So this is all about the finding angular momentum. I think all of you have copied this one. We'll go next. If you have copied this one, then